All right, team, let's get right into it. Today, we're doing a deep dive into our newly ratified Silk Shell architecture and going over the recent critical fixes we just deployed to the Sex Saasos microkernel. As fellow engineers on this core team, you all know exactly how many hurdles we've had to jump over to get this desktop shell fully isolated and race-free. So we're going to unpack exactly how we actually pulled off a zero-copy, mathematically sound UI using physical Intel memory protection keys, and maybe more importantly, how we squashed those catastrophic bugs that nearly derailed our whole last sprint.
Here's a quick look at the agenda. We'll start with the Silk Shell architectural invariants, move into the frame-driven actor system, trace our proven event pipeline, do a post-mortem on those black screen and capability fixes, and then wrap up with our roadmap for hardware and apps.
Okay, part 1. Silk Shell architectural invariants, the absolute strict laws of the microkernel.
Look, we always have to remember the reality of what we're building here. This is a bare metal single address space operating system. We've got zero POSIX assumptions. None. There's no standard, no libc, and definitely no traditional threads. We rely entirely on strict Intel MPK isolation. Every single capability has to be routed strictly through PDX IPC. And, for the UI layer specifically, Silk Shell is a pure state producer, meaning it will absolutely never write to the frame buffer directly. Only the renderer server, Sexdisplay, is actually authorized to do that.
I mean, it's literally right there in bold in our agent_readme_first doc. Any deviation from these rules completely shatters our Ring 3 isolation boundary. Every cross-domain pointer is just straight up invalid unless the kernel explicitly capability maps it. We're enforcing all of this at compile time with Rust's type system, making sure those memory boundaries are absolutely bulletproof before our code even touches the hardware.
Moving right along to Section 2, the frame-driven actor system. This is our contract.
Thank goodness we finally ditched that broken, Wayland-imitating Damon model. It was so chaotic, way too stateful, and just a breeding ground for race conditions. Instead, we've successfully shifted to a mathematically sound, frame-driven actor system. Now we have strict frame tick ordering. Every single frame is its own closed execution quantum. Silk Shell is completely stateless between frames now. It doesn't try to remember historical UI states at all. It simply reacts to the current epoch and computes exactly what the UI needs to look like right this second.
And that brings us to UUIR, our Universal UI Intermediate Representation. Silk Shell acts strictly as a state reactor now, so instead of hauling massive, raw bitmaps across memory domains, Silk Shell just drops light-late scene intent into a shared memory ring buffer. It's literally just appending instructions like, draw a purple box right at these coordinates. The compositor picks up that intent and flattens it straight to the GPU. It totally bypasses that massive syscall overhead that usually just kills microkernel performance. It's a real game changer.
All right, Section 3, the proven event pipeline. Let's look at how this works in reality.
So how does this theoretical contract actually translate end-to-end? Let's trace it. Hardware HID events come in from Sex input. They hit the Silk Shell event reactor, which crunches that and spits out our UIR scene intent. That intent then has to cross the PDX capability edge using slot display, specifically via opcodes like op_window_create. And finally, it lands at the Sexdisplay display state reduction engine, which fires off the atomic commit to the hardware.
This setup is just brilliant for how Protection Domain 3 operates, totally locked down under PKey 3. Silk Shell handles the entire Silk bar layout, all the dynamic workspace switching, and some pretty complex gesture input handling, all under physical Intel MPK locks. Thanks to zero-copy capability handover, the kernel just runs WRPKRU instruction, giving the compositor instant read access to the shell's memory. Not a single byte gets copied, and we literally never miss a frame. Okay, Section 4, black screen and capability fixes. Time for a quick post-mortem on those bugs.
So picture this. We successfully locked down the P keys. The hardware isolation is fully engaged. Awesome, right? But then, we boot up, the compositor graph fails to render a single pixel, and we're staring at a completely headless black screen. Why on earth did that happen?
The diagnosis here was wild. The hardware was locked perfectly, but our software routing table was totally empty. The kernel tagged the frame buffer pages with PKey 1 for Sexdisplay, sure, but it completely skipped the capability grants during initialization. So, without that IPC edge, Silk Shell was physically locked out from talking to the compositor. We fixed that massive black screen issue by statically granting slot display right in the init.rs spawn path. Boom! Software capability edge physically wired to match the hardware locks.
And then,
Oh man, the Ring 3 null-pointer jump. We saw serial logs catching a page fault at RIP jumping straight to address 0. Basically, Silk Shell tried to initialize its display client, but the display slot wasn't resolved, handed back a null pointer, and instantly tanked the domain. We fixed that by writing pdx compositor client.newSafe, which forces strict capability validation before any dereferencing happens. Oh, and while we were in there, we killed a nasty ABI hazard. We stopped using RAX0 as a vague no-message flag and moved to a strictly typed PDX message struct where type ID equals OXOX is explicitly invalid. Those ghost crashes? Completely gone.
Lastly, we had to deal with IPC priority inversion starvation. Under a heavy load of capability graph resolutions, domains were just spinning out. To fix that temporal instability, we made the boot sequence mathematically deterministic by mandating cooperative forward progress scheduling. Now, if the service isn't ready and throws an ERR, service not ready, a sys yielding is structurally required. It instantly punts CPU time back to the initialization sequence. It completely immunizes the OS against those priority inversion lockups.
Finally, Section 5. Next work. Let's look at the roadmap for hardware and apps.
We've got incredible momentum right now, and our next steps are super clear. Up next is Phase 26, where we physically connect sex input normalized pointer events into Silk Shell so we get actual real hardware mouse drag and resize proofs. After that, Phase 27, we're wiring Liner, our file manager, in PD2 via slot storage. And then the really fun stuff in Phase 28, dynamic app spawning. We'll use the app launcher via SecShop, eating up PDX slots 7 through 15 sequentially to spawn real ELF binaries right onto the desktop.
So here we are. We've totally cracked the foundational desktop shell architecture. The IPC capability graph is materialized, and those physical Intel MPK locks are fully engaged. We are running a pure zero-copy UI natively in Ring 3. But now, the big question for all of us is, are we disciplined enough to keep these exact strict invariants in place as we scale this out to the rest of the userland stack? That's our challenge for the next sprint. Let's get back to it.